Hello everyone. Welcome back to my channel, Chemical Adda. In today's video, we are going to learn about solid-liquid equilibria in leaching, or practical equilibrium in leaching. If you haven't watched our previous video on leaching, make sure to check it out first. The link is in the description box below. It will help you to understand the basics of leaching process before we move into this topic. In this video we'll cover: what is leaching? What are the important terms used for graphical representation? Then graphical representation of equilibrium conditions. And what factors affect the leaching process? Now, let's get started. So first let's understand what is leaching. So as we know, leaching is a process where a soluble substance, solute C, is extracted from an insoluble solid, B, using a solvent, A. This process is widely used in chemical, food, pharmaceutical, and metal extraction industries. And, to analyze and optimize leaching processes, we need to represent equilibrium conditions graphically. So, in order to understand how this works, we use graphs to do calculations, just like we do with other mass transfer operations. For this, it is necessary to show the equilibrium conditions on a graph. So, we know that leaching involves three component systems: a pure solvent, A, an insoluble carrier solid, B, and a soluble solute, C. Hence traditionally, triangular coordinates were used to represent the proportions of the three components in the ternary system, or to perform mathematical calculations to determine the composition of each component in the system. But, it has often become too congested in some areas of the graph, making them harder to read. Hence now rectangular coordinates are used instead of triangular coordinates. Now, let's understand how to plot leaching equilibrium on a rectangular coordinate system. For that, first let's see important terms used in graphical leaching equilibrium representation. Let B is equal to mass of insoluble solid or inert solid in kilograms. C is equal to mass of soluble solute in kilogram. A is equal to mass of pure solvent in kilogram. X is equal to weight fraction of solute C in effluent solution on B-free basis, where X is equal to C divided by A plus C. In simple terms, X shows how much solute C is dissolved in the liquid. Then, Y is equal to weight fraction of solute C in the solid, or slurry, or sludge on B-free basis, where Y is equal to C divided by A plus C. Hence the value of Y indicates all solute C associated with the mixture, including that dissolved in the solution, as well as undissolved or adsorbed solute. Now, let N be the concentration of insoluble solid B in any mixture or slurry, which is expressed as N equal to B divided by A plus C. Now, let's discuss what will be the value of N, Y, and X in two extreme cases of leaching, which help us in understanding practical equilibrium conditions in leaching. So the first case is dry solid before leaching. In this case, solid is completely dry before the leaching process starts. That means there is no solvent, A, present in the system. That's why we can consider A is equal to 0. And therefore, the denominator of formula of N will be consist only of the mass of solute C. Hence we get N is equal to mass of B divided by mass of C. Again in this case, all the solute C in the system is present in the solid phase either as undissolved or adsorbed solute. Hence no solute is dissolved in the liquid because there is no liquid yet. Hence, we get Y is equal to 1. Now let's consider second case, where solvent is pure. So, in this case, the system contains only pure solvent A, before coming in contact with the solid B or solute C. That's why, we can consider B is equal to 0 and C is equal to 0. So, after putting the value of B and C in the formula of N and X, we get N is equal to 0. And X is equal to 0. Now, let's understand how we represent these conditions graphically. Hence the graph describes the process of solid-liquid extraction, that is leaching, and showing how the solute concentration changes as the process progresses. Here y-axis represents the mass fraction of insoluble solid B, that is, N is equal to mass B divided by mass A plus C. And x-axis represents the weight fraction of solute C in the solution on B-free basis with values ranging from 0 to 1. Where 0 means no solute is dissolved and 1 means maximum solute concentration. Then point M1 represents a mixture in which all of the solute C has dissolved in solvent A, while only the insoluble solid B remains undissolved, either suspended in the solution or settled at the bottom. At this stage, the solution is in equilibrium, which means that no more solute can dissolve under current conditions. This is an important reference point for leaching because it tells us when extraction is complete. Then point NM1 represents the mass ratio of insoluble solid B to solution. Now, if the mixture is allowed to settle, and the solid is non-adsorbent, then we will get two streams. First one is the clear solution, which is represented by point R1, and second one is the settled sludge, which is represented by point E1. Since the composition of the solution in the sludge will be the same as that of the clear solution withdrawn, hence we can assume Y equals X. Then point NE1 represents the concentration of solid B in the sludge. And its value will depend upon the time of settling. Then, the tie line E1R1 is a vertical tie line, joining the points which represent the two effluent streams, clear liquid and slurry. Now let's see what will happen if settling time for leaching is less. So, if less time is allowed for settling, the sludge will be less concentrated in insoluble solids, and may be represented by an E1'. Now, let us see the effect of initial slurry on concentration. So we know that the final concentration of solid in sludge depends on how much solid was in the initial concentration in the slurry. And that's why a different initial mixture M2 settling for the same time θ1 may result in a different sludge composition E2. What if there are imperfect settling conditions? So, if the solid does not settle completely, or too much solution is removed from the sludge, or some solid B dissolves to a small extent in the solution, then point R2 represents the withdrawn solution's composition, which is B slightly above the lower axis. That's it for today's video on solid-liquid equilibrium in leaching. In this video we covered leaching fundamentals, graphical representation of equilibrium conditions, extreme cases in leaching, effects of slurry concentration and imperfect settling. I hope this video helped you to understand this topic better. If you found it useful, please like, share, and subscribe to Chemical Adda. Also, let us know in the comments if you have any questions or topics that you'd like us to cover next. Thanks for watching, and